All right, so how do we represent our real numbers? Well, as I said the other day, all real numbers can be placed on our number line. So we could describe them geometrically then. No, and all geometrically means is a picture. Because we could draw the picture of the number line and plot the points wherever we'd like them. But we can also describe them algebraically. So we might say x equals this or what have you. Another way we can do it is what's called interval notation. That's very common when we're talking about domain and range of functions and things like that. And another way we could do it is set notation. Right? So we could actually describe the set of numbers. So types of intervals. We can have what's called a bounded interval. So we've got all the numbers on the number line, but it's bounded. And that just means that the interval has two endpoints. So it starts somewhere and it stops somewhere. Of course, it could then be unbounded. And it's going to be unbounded if it only has one endpoint. So it keeps going forever in one of the directions. Closed is when the endpoints are included. And open is if you've got an endpoint that's not included. And then you could have a degenerate. Right? So a degenerate is just a single point. And so we have this one. X is greater than 5. So if I was to put it on a number line, I would draw something like that. It's not equal to, so I just draw the open circle, and we draw an arrow in the direction that we're going. So that would be a geometric way of representing it. It's open, and it's unbounded. So it's an open, unbounded interval. In interval notation, we would write it like that. So when the endpoint is not included, we would draw a parenthesis. When it's included, we draw a square bracket. So that's telling us it's starting at 5, but 5 is not included, and it goes all the way up to infinity. And of course, you can't include infinity because theoretically, you'll never get there. And in set notation, we'd write it like that. So in braces, we say x, the colon means such that. So we want all the x's such that x is greater than 5. Right, x is less than or equal to 6. So this time we colour in the circle to indicate that that point's included. So this time it's closed. Still unbounded because it's going off to infinity in one direction there. And so that's where we use the square bracket with the 6 because we're saying, no, we're including the 6. And in set notation, all the x's such that x is less than or equal to 6. All right, x is in between 4 and 6. But in this case, neither the 4 or the 6 are included. So that's open. It is bounded because we've got these endpoints, but it's still open because the endpoints aren't included. So it's open, bounded interval. So 4, 6, it looks like a set of coordinates, but it's not. I mean, it's telling us it's 4, 6. Parentheses are telling us the endpoints are not included. So it's all the x's such that they're in between 4 and 6. So x is in between -2 and 1, and this time the endpoints are included. So we colour in the circles. So that would be a closed bounded interval. So we use the square brackets, -2, 1. So all the x's such that -2 less than or equal to x, less than or equal to 1. Now the fifth example there, one of the points is included and one's not included. So that's just a bounded interval. That's just called a bounded interval. And that's how we would write it. Parenthesis on the 2 because it's not included, and a bracket on the 4 because it is included. All right, so let's talk a bit more about rational numbers. Remember, they're all the ones that can be written as a fraction where a and b are both integers and can't be simplified down, I guess. Another word for can't be simplified down. Does anyone know that? You've got two numbers that neither goes into the other. Do you know what we call those? Okay, the word is coprime. So if numbers are coprime, then none of the numbers will go into the other numbers. So here we're only talking about two numbers, but you could have several numbers that are coprime and none of the numbers would go into each other. Irrational numbers. Well, they're the ones that are not rational, hence the prefix er. I guess er must mean not. So every irrational number can be expressed as a unique infinite decimal. The classic, of course, is pi. It keeps on going forever and ever and ever. It never repeats. You go along and you think you've got a repeating because here's a pattern, but then it breaks out of the pattern and starts doing something else. So all irrational numbers are like that. It'll go on forever and ever and ever, and it will never repeat. We're going to prove that the square root of 2 is in fact irrational. And the technique we're going to use is what's called proof by contradiction. And when you do a proof by contradiction, you actually assume the opposite to what you're trying to prove. So we're trying to prove the square root of 2 is irrational, so I'm going to assume it is actually rational. Now, if it is rational by our definition of rational numbers, it means I can write it as a fraction, where a and b are integers with no common factors, or as I say, you could say where a and b are co-prime. Well, playing around with that fraction, that means that a is b times the square root of 2. So if I square both sides, a squared is 2b squared. So therefore I know a squared is divisible by 2. Because b squared must be an integer, because b is an integer. Square an integer, you'll get an integer. So a squared is divisible by 2, but hang on a sec. We're talking about prime factors. If you think of prime factors, anytime you've got a square, factors will appear twice because you're saying a number multiplied by itself. So any factor must be there so it can go times itself. So if a squared is divisible by 2, then it must also be divisible by 4. Because if 2 is a factor, there must be another 2 in there so it can be multiplied by itself. 2 times 2 is 4. Well, that means 2b squared is 4 times some integer. That's what k is just some integer. Well, that means b squared is 2k. Well, if b squared is 2k, that means both a squared and b squared are divisible by 2. And so they have a common factor. But hang on, right at the start we said a and b have no common factors. And there's your contradiction. We started off saying they have no common factors, but yet proved they must have a common factor. So the square root of 2 can't be rational. And if it's not rational, it must be irrational. So that's a proof by contradiction. Let's talk about significant figures. As I said, you can't work out irrational numbers exactly because it goes on forever. That decimal keeps going to infinity. So it's impossible to work out the exact amount. Depending on what we're doing with the number, certainly in something like science, you're going to use an approximation. Because you can't write it down exactly, so all right, we'll use an approximation. So when we approximate, we usually write it to either a certain number of decimal places is often useful. Mind you, in science, they tend to go for significant figures rather than decimal places. So a certain number of significant figures. So how do we round off? Whenever you're rounding for significant figures, instead of starting at the decimal point, you start at the first non-zero digit. And then you just count the required numbers and round as normal. So all right, we're going to write these to the given number of significant figures. Here it is, 0.050703. If I wanted to do that to 2 significant figures, I would start at the 5, that's the first number that's not 0, and round off at the next one. So we get 0.051. To 3 significant figures, well, it'd be 0.0507. To 4 significant figures, 0.05070. Now when we're talking about significant figures, we write that 0 down because it's telling something about the accuracy of the measure. I mean, it might have been our measuring instrument landed right on the division, but we put the 0 there to indicate, but that's how accurate I could measure this. Now, whole numbers are always interesting. If I wanted to do 3,000 to 2 significant figures, it would be 3,000. You start at the 3 and then round off. But I've got to put the other zeros there because otherwise I'd have 30 and I've changed the size of the number. If I did it to 3 significant figures, it would still be 3,000. Well, this time I've got to put the last 0 in there. All right, well, 4 significant figures, it's going to be 3,000. So regardless of whether we're talking about 2, 3 or 4 significant figures, we get the same answer. And that's why we have a thing called scientific notation or standard notation. Because when we put in that, then we can indicate how many significant figures. I mean, the first one would be 3.0 times 10 cubed. The second one would be 3.0 3.00 times 10 cubed, and the last one would be 3.000 times 10 cubed, and that's how we can tell how significant the different numbers are. So if it is an ambiguous one, like our whole numbers then, scientific notation is a better answer. Well, how many significant figures are in a number? How do we work that out then? Same idea, we'll start at the first number that's not a 0, and we'll count to the end of the number. So here it is, 0.050703. How many significant figures does it have? Start at the 5, count to the end. We've got 5 significant figures. 0.010031. Start at the 1, count to the end. 5 significant. 0.01000310. Start at the first number, count to the end. Now, that 0 they've placed there, we're counting it at the end because it's there for a reason. It's telling us about the accuracy, so it is significant. So we have 6 significant figures. Whole numbers then, what do I do? Well, has it got 2 significant figures? Has it got 3? Has it got 4? Well, if I'm ever asked something like that, yes, it's 2, 3 or 4. I don't know. It's going to be one of them. If I'm forced to make an answer, I'm going to say 4. I might not be right, but I can't be wrong. So I might not be right, but I can't be wrong. If that's all the information they've given me, I'll say, oh, well, there's 4 significant figures there. If they haven't put it in scientific notation, I'm going to say 4. Use the biggest one if it's ambiguous. As I say, you might not be right, but you can't be wrong. Alrighty, that's the first bit of theory for today.